Alright, so the two numeration systems that I'm going to be comparing to our own Hindu Arabic decimal system is the Mayan system, Mayan numerations, and the Roman numerals. So, really going to focus on the Mayans because it's more complex. There's more that goes into it than the other two. Hindu Arabic is really simple. Obviously, the math associated with it is much more complex. The Hindu Arabic system unlocks so much potential with math, um, but just in the numeration system itself, just counting, um, the base 20 Mayan system is a little more complex than the other two. So I'm gonna focus on that and really compare and contrast the Hindu Arabic system and the Roman numerals as I go along. Um, so a little history to start off with. Mayan civilization popped up around 2000 BC. It's estimated that this numeration system, their system of math, was really fully developed, um, at least developed to a complex, sophisticated level around 700 BC, because that's when we see an explosion of architectural feats and big monuments and buildings, temples, things of that nature. So, um, so yeah. So to start off with, here's the Mayan numerals. They're pretty simple. They seem pretty simple, but don't let their simple nature fool you. They're very very complex, and it has they've the Mayans developed math that is just as sophisticated and complex as our own system. But to really understand their system, kind of have to understand our system first. So the numbers that we use today are called the Hindu Arabic numerals. They originated in India, but it wasn't until they made it to the Arab people in North Africa that they were really transformed into the symbols that we use today. It's these 10 digits, 0 through 9, and it's with these 10 digits that we can really make any number that we want. We can make numbers billions, trillions, quadrillions, exotic numbers like pi, and that's really what makes the Hindu Arabic system different than any other numeration system. Um, um, like if we talk about the Roman numerals, um, they have 7 main different symbols for 1 to 1000, and they have a subtraction property that goes in with that, and I'll get into that later. But problem with this method is as you get larger, you have to constantly create new numbers. You have to create new symbols, and more symbols have to be memorized. It's just really hard. It's really hard, and it gets tedious to write it all out as well. So the Maya only needed 3 symbols to express any quantity. This shell, a dot, and a bar. Okay, a dot represents 1, bar represents 5, and the shell represents 0. They also did their math, or they structured theirs from bottom to top rather than left to right, how we do it. And it was really this right here, this shell, this placeholder, this 0, that was the most important accomplishment of their entire mathematical system. And we'll get into that. So, like I said before, they operate on the base 20 system. A lot of it's thought that they use a base 20 system because that's the total number of fingers and toes that we have, just like it's thought that we use a base 10 system because that's the total number of fingers that we have. So just a different way of looking at it. So because they're in a base 20 system. Well, first let me talk about that 0 and why that's so important. So let's look at the number 25 in Hindu Arabic. Okay, look at the number 25. This is just in base 10 and just normal base 10 Hindu Arabic. 5's in the 1's place, 2 is in the 20's place. So what this really is the 2 is in the 10's place. So that's 2 10s. So what that really is 2 times 10. Okay, and that's going to be 5 times 1. And you add them together to get 25. Or you can write that as 2 times 10 to the first power. But we don't really want to get into that. It was just a number so small, so we don't do that. But that's another notation that you could write that in. In base 10. In base 20, same number. And we're going to do this with the Hindu Arabic numerals, but we're talking about the Mayan system. We're going to use Hindu Arabic symbols to explain it, but we're talking about how the Mayans used their base 20. So this 5 is still going to be in the 1's place. It's still going to be 5 times 1, or 5 times 10 to the 0 power, but that's still going to be the same. This, however, is going to be in the 20's place instead of the 1's place. So this is 2 times 20. So this number is really 45. And that's really it broken down simply in expanded notation anyway. And you can do this. You do this with all numbers as you continue to add on place value. But we'll look at the number 205 now instead of 25. And this is why that 0 is so important, because without the 0, there's no way to differentiate 205 from 25 if we don't have the 0 to hold the 10's place. So the 5 is still in the 1's place. This 0 is place holding nothing. There's nothing in the 10's place, so it holds the place it holds that place for 0. It will represent 0 times 10, 0. Okay, which allows us to see that this 2 is in the 100's place, not the 10's place. So we can see the difference between 205 and 25. So this becomes 2 times 100, or 2 times 10 to the second power. And that's why that clam, that shell, I like to call it, I think it's clam, but apparently it's a shell. But that's why that's so important. That's why their numeration system was able to flourish and be as advanced and sophisticated as it was because they had that 0. So I can show you what happens when we're adding. We'll just go ahead. Show you what happens when we're adding in Mayan. We have dot, dot. It's almost like we're counting tallies. Okay, count tallies. We get to 4, and then we cross it to show that 5. But instead of crossing what we already wrote down, we would just, if we already know the number that we're trying to write down, instead of writing out all those tallies to do, we just write the bar, and that represents 5. And keep on adding. You can't do, when you get to 4 bars, that's 20. Okay, 20 means you need to go, because we're in base 20, you need to go to the next place value. So in Hindu Arabic, when you get in base 10, when we're at 9, and then we count to 10, we move the 0 into the ones place to hold the place of nothing being in the ones place, and we put the 1 in the tens place to show that that is 1 times 10. Same concept in the Mayan system, except instead of going left to right, they go top to bottom. So when we get to 4 bars down here, we move them up. They go up and become a dot. So we would write that out as 20, 20 being the 1 dot up here. But then we have to put that clam, that shell, down here to hold the place value. That's our 0. 10. And we can do this with any number. We can do this with any number. So let's get really big. Let's show the number 5,555. Okay. 5,555 in base 10 is exactly that. It's 5,555. Okay. Its expanded notation is 5 times 10 to the third power plus 5 times 10 to the second power plus 5 times 10 to the first power plus 5 times 10 to the 0 power. That's 5,555. In base 20, however, what we would do, because we're not in base 10 anymore, we're in base 20, we change out the base. We change out the base from 10 to 20. So this number, 5,555, would be written out as 5 times messing up. This is 5 times 2 to the third power, or 2,000. Okay, plus, because that's in the thousands place. But just like here, 5 is in the thousands place. So it's 5 times 1,000. It's 5 times 1,000 equals 5,000. Plus 500, plus 50, plus 5. And that's how you get that number. That's what that number really represents, is each place value. Each place value. And that's why that 0 is so important. So if we keep writing this one out, it'd be 5 times 200 plus 5 times 20 plus 5 times 1. And that would get us 5 times 20, 2,000, 10,000 time plus 1,000 plus 100 plus 5 gives us 11,105. Okay, and that's what that number would represent in Mayan notation. So in Mayan notation, we would have the number 5,555. We're going to write it top to bottom because that's how the Mayans, that's how they do it. So we're going to write it top to bottom this time. And we're going to write exactly what represents 5 in each space. plus 1,000 plus 100 plus 5 gives us 11,105. Okay, and that's what that number would represent in Mayan notation. So in Mayan notation, we would have the number 5,555. We're going to write it top to bottom because that's how the Mayans, that's how they do it. So we're going to write it top to bottom this time. And we're going to write exactly what represents 5 in each space. Alright, so talking about the Mayan system and the Hindu-Arabic system, they both use an additive property, and where they're adding place values together. With the Hindu-Arabic, or with the Mayan, you're essentially adding your tallies up, or your dots and lines, and then adding up your place values. There's not any subtraction going on in just the numeration system, not in the mathematics, but in just the counting your numbers. There's no subtraction going on. In the Roman numerals, however, there is subtraction going on. So the Roman numerals, they use seven main numerals. They use an I to represent 1. They use a V to represent 5. They use an X to represent 10. They use an L to represent 50. A C to represent 100. And this is where I feel like I'm missing one. 5. D is 500. And then we have M equaling 1,000. So these are the 7 main Roman numerals, and basically how they're different from the Hindu-Arabic and Mayan system is with that subtraction property. So if you wanted to create the number 3, you would write 3, and that would equal number 3. However, if you wanted to make a number like 6, do V, put an I in the front to show that we're adding that 1. That would be 6. That's 5. 5 plus 1, 6. However, vice versa, if that 1 came before the V, that's showing 5 minus 1. That's going to be the number 4. So we see that in where the smaller numeral is comes before a large. It's always going to be a smaller numeral after a larger numeral. So when a smaller numeral is written before a larger numeral, and I have to understand that that's the subtraction property that we're talking about. So if we had if we had a number like XLIV, this X comes before this L, and this I comes before the V. So we have to group these two together to show that subtraction. Group these two together to show that subtraction. And it's essentially these two groups being added together. So that's going to be 50 minus, excuse me, 50 minus 10. Because this 10 is coming before this 50. And then the 1 minus the 5 gets you the number 44. Okay, so for instance, like XXVI would equal 26. You have a lesser or an equal after. So it would be 10, 10, 5, 1. You just add them all up. If you had a number like XXIV, that would be now 24. You have 10, 10, 1, 5. So because that 1 comes before that 5, you have to group those together, subtract 5 minus 1, and get that 4 for the 24. However, they did also put some limitations onto what you could subtract. You could only subtract 1, 10, and 100. So you'd never see an LV or a VL. You would never see anything like that. You'd never see a 5 subtracting from anything. So that's one limitation they put on it. Another limitation they put on was you couldn't take from anything that was more than 2 steps away, more than 2 places away. So, for instance, you couldn't write IC to make 99. That would not work. Okay, to make 99, you have to write XCIX. So you have this X subtracting from the C again, X subtracting from the C, and then you have the I subtracting from the X. 2 steps away, 2 steps away. We got that. Okay. So we would take 100 minus 10 plus 10 minus 1, or essentially 90 plus 9 to get 90. 99. Oh. Cool. Right down here. You see how that works? Awesome. Let's see what else. Oh yeah, the other thing that they used was a line over a digit. Let's say you have the number xi. Just write xi, and that's 10 and 1, so that'll be 11. But if you had the number xi written with a line, it would be more like this, actually. If you had that written with a line over the top of it, that signifies that we're multiplying this number by 1,000. So this would represent, this symbol right here, the xi with the line over it, would represent 11,000. So you can get to some pretty big numbers pretty quick. Like if we did the M which represented 1,000 with a line over it, just like that, that would be 1 million. And that's really, that's it. That's really all the similarities, differences between the Mayan numerals, the Hindu Arabic numerals, and the Roman numerals.